So now we're going to talk about some essential functions, functions that you should just know. The very basic ones, right? And I know you know all these. You should know what they look like. You should know, what's going on with them. All that. Let me hold on, make sure I get them all. Okay? You should be able to graph the basics. Like, if you have something crazy like sine of 3x plus pi over 6, blah, 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 whatever, that's fine. Like, I know you can graph that given time, but you have a graphing calculator, you can graph that on your calculator too. But if it's just sine of x, I expect you to know how to graph sine of x without any issue. Okay? So, starting with the basics, linear functions, right? Lines. So, y equals mx plus b is our standard, right? M being rise over run, m being your slope, and b is your y-intercept. So this is slope-intercept form. Okay. Often in this class, because when we're talking about tangent lines, I will use point-slope form. I don't know how many of you like this. You do not have to use it. You can use slope-intercept, whatever you can work out. But point-slope form of a line, if you know the point, and you know the slope, so our slope is m and our point is x naught, y naught, we can write down the equation of the line y minus y naught equals m times x minus x naught. Okay? And then we can turn this very easily in slope-intercept form, right? Because that one just goes on the other side and whatever. I will use this when I write down, when we figure out the tangent line formula, and then I'll use this. You don't have to. You can do it whichever way you want. Like, you can do whichever way you want. But this is just so you know what I'm doing. I will often use this. Okay? So that's a line. Remember, the horizontal line has slope 0. As I move up this way, my slope becomes more positive. If I move down this way, my slope becomes more negative. So this is this guy. This one, of course, is just y equals what we call this b. Right? And what about a vertical line? A vertical line, we can say, has infinite slope, right? Because it's going on it. And the vertical line then has formula x equals a. So a little bit different, right? Vertical line fails the vertical line test, right? Because it's a vertical line. So it's not a function. But it's important anyway to know the vertical line, right? All right, so there's lines. Now we'll talk about the monomials. So monomials, you're just going to look at things x to the n, right? It's only got that one term. So we'll start with y equals x squared. Looks like this. Y equals x cubed. Looks like this. Right? I apologize. I don't have colored chalk that actually works on, like, you can't see it on YouTube. I mean, I bought the expensive colored chalk, but it's basically worthless. So, sorry about that. What ends up happening, right? Let's look at these. Let's say this is 1. And this is -1, right? So all of these will go through 1, 1. Here too. It's going to go through 1. And here, of course, because it's the cubic. Yeah. Trying to make it look reasonable. That didn't really draw that very well when I drew it freehand. Okay, we got -1 here. Okay, so that's y equals x squared. Now, what's going to happen when this exponent grows? Okay, so if I do y equals x to the 4th, and I'm going to use dotted lines, what's going to happen is this is going to be less than that. It's still going to go to 1, and it's going to go up faster. So your even ones, as your power increases, this gets closer and closer to flat, and this gets higher and higher like that. And similarly with the odd powers, right? This is going to be flatter and steeper, and flatter and steeper. So those are the families of curves. They look fairly similar, right? I'm not sure how well the dotted line even looks on the screen, but you get the idea. I mean, this is all review. You should know this anyway. Okay, so it's sort of important to have that idea. That's how those monomials look. Right? I'm calling it a monomial because it has only that one term, right? If I have a polynomial, then it's got a whole bunch of other terms. So then you've got something, whatever. That's a polynomial. I have no idea what that looks like, okay? Off the top of my head, I can't graph that. I would either, well, I could put it in the calculator if I had one. I'll use Desmos, or use calculus techniques, which we'll learn how to use calculus techniques to figure out how to draw this picture. But on the face of it, I don't know what that looks like. It's a polynomial. So speaking of polynomials, a polynomial, just in general, let me be clear. If I write a general form of a polynomial, I can write it like this. Okay, the leading term is the term with the largest power, right? That's the order of the polynomial. This polynomial of order 4, this polynomial of order n, right? These are the coefficients of the polynomial. My leading coefficient here, an, here it's 3. Many of these can be 0. Like here I put in all of them just for kicks, but all the coefficients can be 0 except for like whatever, the first one is the first one, right? So that's sort of standard thing. They call that the constant coefficient. I think that's about all I can say about polynomials. Okay. What else? So there's polynomials, root functions, right? So y equals square root of x. We will have a nice long discussion about this, right? Because we can't take the square root of a negative number. So there's none of it over here. Write the domain. The natural domain is all the non-negative numbers. In fact, we had to do that just to define this as a function. And we'll talk about that when we talk about inverse functions. So whereas, of course, if I look at the cube root, that's not a problem. I can take the cube root of a negative number. So this just looks like that guy. And the same thing is going to happen as I take the numbers up, right? So I can think of this as being x to the 1/2, and I can think of this as being x to the 1/3, right? So if I take the 4th root, again, this is going to go through the 0.11. If I take the 4th root, so we'll do y equals x to the 1/4, dotted line. It's going to be steeper here. It's still going to go through the 1, 1, and then it's going to go like that. If I do y equals x to the 1/5, it's going to do the same kind of thing. Because, again, as you know, these are inverses of the power functions, the monomials that we were just looking at a minute ago. Okay? So that's very straightforward. Now, let's see what else we have. We've got some reciprocals. All right? Now we have something new, y equals 1 over x. Again, I've got this domain issue, right? Because I can't divide by 0. So my domain here, I got to get rid of 0. 0 is my vertical asymptote. And it's sort of hard to see. Sorry about that, but you put a dotted line to show that it's a vertical asymptote. And what you will see, of course, if you graph this, is that it does this. And I probably didn't do that well enough. I should have made it bigger. Let me make it bigger. Because if I'm going to put 1 over x cubed on, yeah. Really make it bigger. Let's make this 1. Okay, so it's doing that. And as you know, as I get very large x's, this is going to get very small. It's going to get very close to 0, but never going to be that. As I have very small x's, it's going to grow very large and positive, very large negative. Never going to actually get there, right? So hence the asymptote. If I look at 1 over x squared, it's pretty much the same story, except for the fact that the squared means that it's not down there, this branch is up there. Right? So I still can't have 0 in the bottom. So I have something like this. Okay? Not a very good graph. I apologize. Again, my domain for all of these, I got to get rid of that 0. Okay? And the same thing is going to happen as with the regular monomials. When the power goes up, if I do 1 over x cubed, it's still going to go through the 1, but it's going to go faster, right? It's going to go towards each asymptote, both the horizontal and vertical. It's going to go towards it faster. And in fact, if I graph this over here, this one goes down faster than this one goes down further. You know, it's just the same kind of thing. So, but they're all going to go through that point at 1, right? So this would be also y equals 1 over x to the 4 dotted. Right? Oh, this video is getting too long. Well, you can watch it on double time. Because this should all be super, super boring review. So I hope you are finding this super boring review. Okay, almost done. We're going to talk about exponential functions and, of course, logarithms. So the exponential function, y equals e to the x, goes through here. Right? Domain is all reals. It goes off to infinity as x goes up, and it goes down to 0, but never touches, right? So you've got a horizontal asymptote on this side, okay? And we'll talk about these in greater detail, but you know those. So then its inverse is y equals natural log of x, which has an asymptote, or vertical asymptote x equals 0, and that does this, right? So if I look at this, of course my domain is all R. If I look at this, my domain, I gotta get rid of that 0, right? I can't take natural log or any log of 0. Well, it's negative infinity. So I have that. I will say, of course, I wrote it e in natural log. It could be b in log base b. For the most part in this class, I like to just use e and natural log, not really worry about base 2 or base 10 or whatever. So these are the ones that I'm going to use. I'm just going to stick with that mostly. You might see occasionally a problem with a 2 or a 3, but it won't happen very often. Okay, last ones are our trigonometric functions. So, and then here's the thing I do want to discuss briefly, right? Trigonometric functions, you know you have the 6 of them. Sine, cosine, tangent, cotangent, secant, cosecant. Do you have to know the graphs of all of them? It's good to know the graphs of all of them. Which ones are we going to use most often? Sine, cosine, tangent. We won't really see too much of the graphs of secant, cosecant, and cotangent. If you have to graph it, you can use your calculator to graph it, but just having an idea of sine, cosine, tangent will be fine, really. So sine of x, just remember sine and cosine are bounded between -1 and 1, right? This is one period, but they are periodic with period 2 pi. So go like this, and we extend that. Okay, so that looks terrible, but fine. Oh, that's sine. Sine of 0 is 0, right? Cosine is moved over. So interesting point about these guys, of course, is that our domain is all of R. Our range is from -1 to 1, unless you have some number before, but we'll talk about that next video. Right? So for cosine, you're here, right? Yep. This is a bad picture too. That's terrible. Ah, it's terrible. Terrible picture. Okay. Sine and cosine. Yeah. So tangent. Tangent is different, right? Because tangent is sine over cosine. So wherever cosine is 0, you are going to have asymptote. Okay? So cosine is 0 at pi over 2 and negative pi over 2. Let me try to put some. This is going to be pi, it's going to be 3 pi over 2. It's going to be minus pi, like I say there, right? So at least it looks reasonable. But remember, because sine and cosine are periodic, tangent is also periodic, but because of the way the signs work out, tangent is periodic with period pi. So you have these different branches of the tangent function, right? And what I don't want to say about it. Oh yeah, so if I look at the domain of this function, I have to break out every one of these, like through pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, so all the odd pi over 2s. All those are all going to be asymptotes. My range, of course, is all of R, right? Because as I get closer and closer there, I'm blowing up. Because if I think about what's going on, right? At pi over 2, sine is 1 and cosine is 0, right? So it's going to blow up. Okay. So those are your very basic functions.